Okay, so let's get started again. So in the last class, some of you had questions about this. If the gradient is going to 0 in one direction, how is the anisotropic diffusion going to save it, right? So let me just quickly clarify this. So the original equation that we had to model is this, right? So dou by dou xj, I'm now talking about the k equation. So dou by dou xj of half of ui prime uj prime. This is the exact term. This we modeled as in the isotropic diffusion coefficient. If you are going to use, then it will be dou by dou xj of, we simply used mu t by sigma k dou k by dou xj. This was the model, right? The sign was missing. I think there's a minus here. Let me see. Yeah, minus. There's a minus sign. Okay. Fine. So here, let's see. So this particular thing, this ui, this part here, ui prime, that is a scalar. Sum of three terms. So that is a scalar. So this is essentially diffusion in three different directions. Okay. So turbulence is diffusive. So it transports in all the three directions. So I would get this particular term as dou by dou x1 of minus half ui prime is a scalar, sum of the three. So I get u1 prime here. So representing the diffusion along the x1 direction and the diffusion along the other direction, dou by dou x2 minus half ui prime average u2 prime plus the diffusion along the third direction minus half ui prime u3 prime. So this represents diffusion in all the three directions, right? Diffusion in all the three directions. This is what we wanted to model here, and this is modeled as using a gradient of the turbulence kinetic energy. So if I expand this in the model, I get dou by dou x1 of mu t by sigma k dou k by dou x1 plus dou by dou x2 of mu t by sigma k dou k by dou x2 plus the diffusion in the other third direction dou k by dou x3. In the gradient diffusion hypothesis itself, we wanted the diffusion to occur based on the gradient of the turbulence kinetic energy. So suppose in reality, in the exact equation, let's say diffusion is occurring in all the three directions, but we have no access to these correlation terms and we are modeling it based on purely statistical approach, that is using k, which is a statistical value, right? K is nothing but ui prime average, right? So this is statistical, a statistical value. So now what if gradient is 0 along x1 direction here? If dou k by dou x1 is equal to 0, this implies diffusion along x1 is 0. This is according to the model, okay? According to the model. And of course, we considered here isotropic diffusion coefficient here, right? Isotropic diffusion model here. So this is giving a problem. If the gradient is 0, then the entire diffusion goes to 0 in that direction. So it may not model appropriately. That's why we introduced the anisotropic diffusion coefficient, which is essentially the option that we had was the same thing. Instead of dou by this part is same, left hand side, ui prime, uj prime. This is now modeled as dou by dou xj of ck k by epsilon uj prime uk prime, okay, and then dou k by dou x k. Here of course k represents, this k represents turbulence kinetic energy here. This is turbulence kinetic energy, and the other k is the index. Okay, so this is turbulence kinetic energy. This is the repeated index k here. You could use m or any other if it is confusing. So now let's see what happens if I expand this. So upon expansion, I would get, let's say, the dou by dou x j of, let's say, the dou x1 term. So if I expand this, I get dou by dou x1 of ck k by epsilon u1 prime, or I can write it here, if I u1 prime, uk prime is also there, and k is repeated. So this is actually sum of 3 terms here, that is just in one direction, it is a sum of 3 terms. So I get u1 prime 2k by dou x1 plus I get plus I have dou by dou x1 of, or I can just simply write it inside, plus I have the other term here 1 1. So I get ck k by epsilon u1 prime u2 prime dou k by dou x2 plus ck k by epsilon u1 prime u2 prime dou k by dou x3. This is only I am looking into one particular direction here, right, just the x1 direction here, dou by dou x1. Obviously this is sum of the 3, so I am looking into only the diffusion along one direction. So you can see, unlike above when we used isotropic diffusion coefficient, it was a single term. Dou k by dou x1 is 0, means the entire diffusion rate was 0. But here in the x1 direction, even if dou k by dou 1 is 0, okay, even if this is 0 here, this is sum of other terms, right. So I'll just write it, I am not expanding it here. So I get plus dou by dou x2 of a term plus I get dou by dou x3 of another term, similar terms here. So now even if dou k by dou x1 is 0, the entire diffusion coefficient is not going to 0, because I still have this term and this term to save me, right. So these are there to help me, the gradient in the other two direction. Even if dou k by dou x1 is equal to 0, the diffusion, the entire diffusion along x1 direction is not 0. That is why this anisotropic diffusion model, this helps in that. So it is a sum of 9 terms actually. So when you look at this, this is this particular term here, sum of 9 terms. In each term there are 3, okay. So this is clear why if the gradient is 0 in one direction, it is still able to save the entire diffusion coefficient in that particular direction, and turbulence is diffusive, diffuses in all or transports in all the 3 directions. Similarly, I have transport in the other direction in x2 and x3. Okay, this is clear. Shall we move to the dissipation rate of turbulence kinetic energy? Okay, fine. So let's look at the dissipation rate of turbulence kinetic energy. Sorry, dissipation rate of the Reynold stresses. What we are modeling is epsilon ij here, epsilon ij model. So now this requires a model. Modeling epsilon ij. So, and what is the formulation for this? Epsilon ij exact, epsilon ij exact in the formula is 2 nu dou ui prime by dou xk dou uj prime by dou xk in the epsilon ij or the Reynold stress equation. So now let us look at each of these components along for each of the stress equation. So say I equal to j equal to 1, that is your u1 prime equation. In this equation I get epsilon 1 as 2 nu dou u1 prime by dou xk dou u1 prime by dou xk average. Similarly, when I equal to j equal to 2, epsilon 2 is, this is for the second normal stress equation, u2 prime average. So it is 2 nu dou u2 prime by dou xk dou u2 prime by dou xk. This is the u2 prime equation. And then I equal to j equal to 3. This is epsilon 3 will be 2 nu dou u3 prime by dou xk. This is sum of 3 terms. I am not expanding the repeated index k. This will be sum of 3 terms here, each of this. Sum of 3 terms. Okay. K is repeated, right? K is repeated index. Fine. So these 3 components are there for the 3 different equations, 3 normal stresses equation. Now we are going to make some assumption here in this part. So what we assume is, we assume that at small scales, okay, so assume at small scales, also we will call it dissipative scales, assume at these small scales, that means turbulence is a multi-scale problem, you have eddies of different sizes. So we are going to assume that at the small scales, at the smaller eddies or the so called dissipative scales, there is a local isotropy. Okay. We will see that later whether such a condition exists, and we are not debating on that. For modeling purpose we are going to assume, and I will discuss more of this dissipative scales and local isotropy when I move to Kolmogorov hypothesis. As of now, just assume at small scales or dissipative scales, local isotropy exists. Okay. Turbulence is locally statistically isotropic. You can say statistically isotropic or local isotropy is there. Local because it is at not in a particular XYZ location, but at these scales, at the so called small scales wherever they are present, local isotropy. If that happens, then what will happen to our Reynold stresses? Okay, so if this condition exists, right, this implies the u1 prime square, u2 prime square are all equal, statistically isotropic, right, and therefore also this correlation term here, all the it's a local isotropy for all the statistical quantities, and here I have a statistical quantity where I am looking into the correlation of gradient of fluctuations, dou u1 prime by dou xk term and so on. So also you get dou u1 prime by dou xk, dou u1 prime by dou xk average is dou u2 prime by dou xk, dou u2 prime by dou xk, dou u3 prime by dou xk. Statistical isotropy or local isotropy will help me say that these three components are same. Okay, that is the assumption we are making here. So now this is not local isotropy at all the scales, only at small scales, okay, only at the small scales here. So with this, what I can say, what will happen to is that each of this component here, so therefore I can say, therefore epsilon 1 I can say is nothing but 1/3 of epsilon II. Can I say this? Okay, I sum it up, divide by 3 is nothing but epsilon 1 or epsilon 2 or epsilon 3. Okay, epsilon 1 or epsilon 2 or epsilon 3 is nothing but 1/3 epsilon I. Okay, so now we look into the other three components in the epsilon ij term, that is when I equal to 1, j equal to 2. This is for the shear stress term u1 prime u2 prime average. This term will occur in this shear stress equation. So epsilon 1 2 will be 2 nu dou u1 prime by dou xk, dou u2 prime by dou xk. Similarly, I equal to 2, j equal to 3, epsilon 2 3 will give me 2 nu dou u2 prime by dou xk, dou u3 prime by dou xk. Similarly, when I equal to 3, j equal to 1, I get epsilon 3 1 or 1 3. I get 2 nu dou u1 prime by dou xk, dou u3 prime by dou xk. All right. So now, when there is statistical isotropy at this small scales, locally isotropy condition, what will happen to the shear stress? Here again, local isotropy at small scales, right, small or dissipative scales. We are assuming here that the small scales are causing the dissipation, not the large scales or intermediate scales. Okay, we will come to that later. But right now we are assuming that these tiny scales are the one which are dissipating the energy or dissipating the stresses here. So local isotropy at small or dissipative scales also implies the shear stress term, which is u1 prime u2 prime, u2 prime u3 prime, u1 prime, u3 prime are 0. Okay, essentially the diagonal components are same, off diagonal components are 0 when you have a statistical isotropy at that scale. If this occurs, then we also have this particular term, which is dou u1 prime by, therefore dou xk, dou u2 prime by dou xk average 2 nu dou u2 prime, or I don't need 2 nus here, dou u2 prime by dou xk, dou u3 prime by dou xk, and so on. This will essentially go to 0. So that means when I is not equal to j, so therefore epsilon ij is equal to 0 when I not equal to j. So using these two, I can now formulate a model here. So therefore I can say, therefore epsilon ij model, I can say, can be something like it has to be 1/3 epsilon ii, but when I not equal to j, it has to go to 0. So what should I do? Kronecker delta ij. Okay, only when I equal to j, delta will be unity, and therefore it will save the normal stresses. For shear stresses, epsilon ij model will give me 0 value. But this doesn't solve all our problems now. We are only one step behind modeling it. What is it? This model is incomplete, right? It's an incomplete model. Why? Do we have access to this epsilon ii component, even one component? Dou u1 prime by dou xk, it's actually a sum of 3 components. We don't have access to the correlation term, right? So we need to model this further. We have to, the whole idea of modeling is relating unknowns to what is accessible to you, right? There are far too many unknowns and you have some known quantities. So you try to relate these unknowns to known and make some arguments. So now we have to continue this further, and I am going to say, okay, so now we have learned that epsilon ij is equal to 1/3 epsilon ii delta ij. At least with that assumption, we have come to this state. But epsilon ij also has a formula, right? Epsilon, okay, epsilon ij, also epsilon ij, the original equation is 2 nu dou ui prime, dou ui prime by dou xk, dou uj prime by dou xk, the exact equation here. This is the model part here. This is the model assumption. This is the exact one, epsilon ij. And if I contract the indices here, okay, contracting indices, or I can write it here, contracting indices, that is setting I equal to j, I would get epsilon ii will become 2 nu dou ui prime by dou xk, dou ui prime by dou xk. Okay, but still we cannot substitute this in equation 1 because these are unknowns to me. Dou ui prime by dou xk are all unknowns. But we also have epsilon exact. Where does this epsilon come? This in the turbulence kinetic energy equation here. This is in the TKE equation, right? Turbulence kinetic energy equation. So I am taking help from that part here, because eventually this epsilon II is sum of the three diagonal components. So I am trying to relate it to the turbulence kinetic energy equation. Okay. So epsilon exact is nothing but nu dou ui prime by dou xk, dou ui prime by dou xk. You would have probably used j and j there, but j and k are free indices, so it does not matter whether it is dou ui prime by dou xj, dou ui prime by dou xj, or replacing j with k. It is the consistently same, because upon expanding it is sum of 9 terms. So now if I look at these two equations, let us call this equation 2 here, and this is 3. So what do I get from equation 2 and 3? So from 2 and 3 I can see that from 2 comma 3 epsilon exact is nothing but half of epsilon II, correct? This is nu of this is 2 nu of this. So this is half of epsilon II here, right? Okay. So now I can substitute this equation 4 in 1. So using equation 4 in 1, I will get my final model, that is epsilon ij model is nothing but, it is 1/3 of epsilon II, which is nothing but 2 epsilon. So it is 2/3 epsilon, delta ij. This is your model. Is the model complete now? Now epsilon ij I am going to substitute it in the Reynold stress equation, modeled equation, and it is 2/3 epsilon delta ij. Where is epsilon coming from? We need a transport equation here. So in the Reynold stress model, one more transport equation is solved for epsilon. Okay. So here epsilon must be solved using modeled transport equation that we have, that is dou epsilon by dou t plus uj bar dou epsilon by dou xj. This you are all familiar in the eddy viscosity model, right? So you have dou by dou xj of what do I have here? The nu plus nu t by sigma epsilon, correct? Dou epsilon by dou xj, and I have the C epsilon 1 pk epsilon by k minus C epsilon 2 epsilon by k. But I do not need a k modeled equation to solve this, right? So here where I have this nu t is coming from k square by epsilon, and k is half of your ui prime average. So you have access to the Reynold stresses here, you are computing for it. So k is computed from that, mu t comes from k square by epsilon, epsilon will be coupled to itself here, and then the pk is also exact, pk is also minus ui prime uj prime average dou ui bar by dou xj. Okay, so this is exact, no modeling required here. This is also exact in the sense it is not giving you back the theoretical value, it is just that these values are coming from still your model transport equation. I am not talking about accuracy here, Okay, so these are at least not modeled. So these terms you can obtain it directly, K and Pk. So it is lot better, it will be a lot better than when you are solving for a K epsilon model here. But this additional transport equation is required. So the RSM models are also called 7 equation model because its 7 transport equations are solved. Okay, so you can say this RSM will totally have 7 transport equation. Six Reynold stresses and 1 dissipation rate of turbulence kinetic energy. Okay. So now we have looked into production rate, which is not required to be modeled, great in Reynold stress model. Diffusion rate, again we have two options, anisotropic diffusion or isotropic diffusion. I told you that anisotropic diffusion coefficient, if you use it, it's numerically unstable for some flows. You can use it or you can fall back to the isotropic diffusion coefficient. That is solved. Viscous diffusion, directly you get it. And dissipation rate is this model, 2/3 epsilon delta Ig. Solve epsilon, you get it. Any term that we missed? Pressure strain rate. Okay, so this will get very intense, this particular term, because we never attempted to model a pressure and its correlation with a velocity or velocity gradient. This term gets very intense in modeling.